Welcome to Fireside Chat number 8 for our experimental design course. We're recording this one as we usually do, and you can find the recording for this one later on, and also the recordings for these 7 previous Fireside Chats in Coursera. It's in the resources tab of the course, and we're going to be posting this recording pretty soon, as soon as we're finished. A couple of things to remind you about if you're a first timer. This is good information. When you come in, your microphones are muted, the videos are turned off. Please don't turn them on. If you have a question that you would like to send in to either me or to our guest, Ron Fricker, please do that using the chat function in the Zoom menu bar. And you don't have to wait until the Q&A session starts. You can actually do this anytime you want. And when Ron is finished with his presentation, we're going to start addressing those questions. And sometimes we don't get them all answered right away, but we will get around to that, and we will respond to them in Coursera for people enrolled in the course as soon as we can after we shut down. Okay, so today we have a very special guest, Dr. Ron Fricker. Ron is the Interim Dean of Science at Virginia Tech, my old alma mater. He's been there since 2015. He was head of the Department of Statistics before he took over the interim dean's job. Prior to his time at Virginia Tech, he was a faculty member in the Operations Research Department at the Naval Postgraduate School. And before that, he was a senior statistician at the RAND Corporation, where he was also associate director of RAND's National Security Research Division. Ron has a brilliant research career. He's focused primarily on various statistical methods for use in disease surveillance, and in general, what we call statistical process control type methods. He's a well-published author in this area. He has over 100 publications, journal papers, monographs, and so forth. And he's the author of 2 books, 2 really excellent books. The first of these was his book, Introduction to Statistical Methods for Biosurveillance, which was published by Cambridge University Press. And I just thoroughly enjoyed reading that book. In fact, he was generous enough to let me use one of the data sets from that book as an example in one of my textbooks. And very recently, he co-authored a book with one of our previous guests, Steve Rigdon. And this book is very timely. It was just published at the outset of this coronavirus pandemic that we're going through. The title of it is Monitoring the Health of Populations by Tracking Disease Outbreaks, Saving Humanity from the Next Plague. This is a really timely topic. And I've asked Ron to talk about some aspects of this in his presentation today. Dr. Fricker has a PhD and an MA in statistics from Yale. And I first met him when he was a PhD student at Yale University. He also has an MS in operations research from George Washington University, and his bachelor's degree is from the United States Naval Academy. Upon graduation from the Naval Academy, he served as a surface warfare officer in the United States Navy. I've always meant to ask you, Ron, were you guns, or were you navigation, or were you engineering? You know, there's lots of different things that surface warfare people do. Anyway, he is a fellow of the American Statistical Association and a fellow of the American Association for the Advancement of Science, and he's an elected member of the International Statistical Institute. He's a very well-known person, and I realize this topic today is not really face on about experimental design, but it is really timely, and he is an internationally recognized authority in this area. So we're very lucky to get his time today. And with that, I'm going to turn this over to Ron Fricker, and maybe he'll tell me whether he was a gunnery officer or not.
Well, thanks, Doug. It's an absolute pleasure to be here. Your introduction was so kind. And I was an engineering officer, I guess, to answer that question.
Good.
That's
what I figured.
But I'll say to the students, you guys are very lucky to have Dr. Montgomery as your instructor here, because Doug, as you I'm sure know, is the authority in many of these areas. And for my career, it's been a wonderful opportunity to know Doug. As we were talking before this session kicked off, when I was a graduate student, he was an editor of a journal, and we first met when I was with my advisor sending an article in, and Dr. Montgomery was so kind and helpful getting that article published. So I don't know, Doug, it's been decades now, right? It's been 25 years or so.
Yeah, at least a long time.
So thank you for everything, including the introduction, but also just your friendship and being a colleague for all these years.
Well, I appreciate your taking the time. You're a very busy guy right now, and I appreciate you taking the time to participate in this fireside chat. And I'm really looking forward to the talk.
Well, great. So thank you. So maybe I'll share some slides. And as Dr. Montgomery said, this is not going to be quite on target for design of experiments, but boy, the last year for me, as I'll tell some stories here in a minute, has just been an amazing whirlwind in the sense that Dr. Rigdon, who I think you saw, it was either late November or early December, he came and gave a lecture. He and I worked on a book, and it came out literally as Dr. Montgomery said, right, as this pandemic hit. And so I want to tell a couple stories about our experiences there, but it's been a whirlwind working through that, following that, and as I'll talk about in the talk here, I'll talk about some of the stuff we've done at Virginia Tech, because we've been intimately involved, as I'm sure people at ASU have, at surviving and working our way through that pandemic as an institution. So I basically said this is from the book, Monitoring Health Populations by Tracking Disease Outbreaks, but really what I'm going to focus on is current events. So let me see if there we go. So as we were talking about, it was back in 2015, fall of 2015, Steve Rigdon and I proposed to write this book about disease surveillance. It's part of a series at the American Statistical Association. It's about kind of statistical literacy. It's intended to be written for general audiences. And both he and I over the years have worked together in various parts of really taking the statistical process control that Dr. Montgomery talked about and applying it to disease surveillance. That's sort of our expertise and our intersection between statistics and quality control and these public health problems. I really started it, back before 9/11, because I was in sort of the defense area, and we were looking at questions about detecting bioterrorist events. But that's really morphed over time, and today it's all about just general diseases, right? The general disease surveillance. But as Dr. Montgomery said, we didn't have any idea back in 2015 what was going to happen in 2019, 2020. We were just working on this book, and we thought it would be interesting for readers to do. So what I wanted to talk about here is really sort of my experiences doing that, and really it's since we've written the book. And by the way, I put on the slides, I guess we've passed these slides out, Doug, to everybody.
They're available.
Okay, great. So the link at the bottom there is to a podcast that Steve and I did, I think it was early December, that talks about the book. So if you were interested in what he talked about before last fall and what I'm talking about now, there's a nice podcast out there, just us talking through it. So I wanted to start, and I have two stories to start with about this sort of strange confluence of the book we're working on and then this pandemic hitting. And what I'm showing you here on the screen is the outbreak as it started in Wuhan, China. So this is coronavirus, and it's starting down here on the left in early January of 2020, and this really just runs through the middle of February. This is data, as the link at the bottom shows, from the World Health Organization. So it's sort of backward looking. This is not what happened in real time at the time. There's a lot of confusion, in fact, if you remember back then. This is data compiled since then about the number of cases in Wuhan. And so you can see that, early in January it was small, but it grew pretty quickly. And the reason I put this on here is because just before this, it was early December, Steve came out to Blacksburg. I'm out at Virginia Tech. He came out to Blacksburg. We were finishing the book. We met at a Residence Inn just across from campus. We had the page proofs and we were going through correcting them. And as we're sitting there for hours drinking coffee and working through his page proofs, Steve says, hey, seems to be something strange going on in China. Maybe we should mention it in our book. And Steve was a smarter guy than me. He was paying attention. So we said, yeah, all right, let's do that. And so we added a single sentence to the book that said, and here's the quote, on November 16th, 2019, Chinese authorities diagnosed a case of pneumonic plague in a 55-year-old man and quarantined 28 people who came in close contact with the man. Now, pneumonic plague is the plague as you think about Black Death. It turns out that was not the story of 2020. That was a true event that was handled. But what we didn't know is at the same time we were writing that of course the coronavirus outbreak was just kicking off in Wuhan. But by early January, of course, everyone knew about that. It was in the news. And so on, by about mid-January, so about a year ago, literally, Steve and I said, oh, we got to add something to the book. This book was due out in mid-February. We got to add something because it can't come out in February. And we completely ignored what's going on in China. So we added to the preface one paragraph, and the paragraph read, and again, I'm quoting what we had drafted at the time. It says, in early 2020, an outbreak of a coronavirus occurred in Wuhan, China. This outbreak may be linked to a seafood and animal market, which was closed on January 1st, 2020. As of mid-January, this is when we're writing the words, as of mid-January 2020, the disease has killed 2 people and sickened more than a dozen. Some passengers at airports in the US, and in quote, San Francisco, LA, and JFK, will be subjected to enhanced screenings. So there we go. A year ago, that's where we were, and that's what we put in the book. Okay, so we're still working on this. We're getting ready for publication in mid-February. A couple of weeks go by and we say, whoa, a lot has happened. Okay, so look on this plot, we're writing those words somewhere right in here. And of course, by mid-January, that's when Wuhan starts up this epidemic curve of the outbreak. So somewhere around here, we say, oh, time out. We actually have to change what we wrote. And so we took out that first paragraph and we added a paragraph to the first chapter that said, in late 2019, a novel coronavirus called 2019-NCOV, that's what we were calling it a year ago, emerged in Wuhan, China. As of early February 2020, the virus had sickened over 30,000 and killed almost 700. In response, quarantines and restrictions on travel from China are being implemented. Time will tell how effective these measures are. Those were our words. Well, of course, we know where that story goes, but that's around here. So, all right, we're a week or two away from this book going to publication. We get over here and we say, stop the press. It's like, okay, that change was dramatic, but it's already changed even more dramatically since then. So we took out the one paragraph. We actually wrote an entire page for which here's the first paragraph. It says, now also, as this book goes to press, the 2019 novel coronavirus is challenging governments and World Health organizations to contain it. As of early February 2020, the World Health Organization has declared 2019-NCOV a, quote, public health emergency of international concern, and travel bans to China are being implemented, borders are being closed, and quarantines are being implemented and enforced. It's too early to tell whether these measures will be fully effective or not. Well, okay, again, here we are now. We know that in fact that was not the case. So this was evolving in real time as we're trying to write this book and publish it. And of course, if you go back, if you get a copy of this book and look at it now, it's ridiculously out of date, right? A year later, what has happened, and I'll show you what has happened in some graphs, doesn't match those early things we were trying to write. But having said that, and again, as you look at the graph, notice the scales. This will be important as we go through. The y-axis here, the top is 4,000 cases. And I don't know if you can read this on your screens or not, but the numbers above each of the bars are the number of cases per day. And it peaks here at about, well, it's just under 3,900 cases on February 5th. But it's in the 2,000 to 3,000 cases per day going forward. Okay, so we start there. Now, the second part of this story is I was trying to finish up the book with Steve because I was heading over to Switzerland to teach in Virginia Tech's what's called the Presidential Global Scholars Program. This is a program by which undergraduates go and do a semester in Europe. It's in what we call the Steger Center. So it's in southern Switzerland. And they go and spend a semester and they get a bunch of classes. And I was teaching a 2-week class, 40 hours, right? So a full class, but in a 2-week time period. for these students about basically statistical thinking, I guess is the way I would say it, in a global context. So get the book done. I'm thinking I got a whole bunch of lectures I got to get done because it's 4 hours a day for 2 weeks straight. I'm trying to get organized for that. I'm focused completely on that, leaving at the end of February. But that happens. And so I get there. And in fact, this is, again, now the time is on the horizontal axis here. This is February 20th now, and it heads up until mid-March. I fly into Milan, Italy. So northern Italy, just over the border from Switzerland. And it's about a 30-mile, 40-mile trip from there to where I had to be in southern Switzerland. Well, again, I'm not, I said Steve's a smarter guy than me. I'm not really paying attention to what's going on. But in fact, if you remember, it was northern Italy, and it's kind of the northeastern part of Italy where the virus moved from China and landed there. And in fact, as I flew into Milan, overnight flight, fly into Milan, stumble off the plane, they're taking our temperatures as we come off the plane. And I'm thinking, oh, they're just being careful. This is great. Get in my cab, I go to Switzerland. But what you're seeing on here now are the cases of the virus as it started to spread through Europe. The blue bars in particular are Italy. And so you can see it starts, and again, by the way, the y-axis, if you can't read this, it's 4,000 at the top. So it's 0 to 4,000. So relatively small numbers down here, but I show up and start teaching. It was either February 21st or 22nd. I don't remember when the Monday was, start teaching. And it was just that Monday or Tuesday when in fact, the numbers started to hit in northern Italy, sort of the Bergamo region up there. They start to go into lockdown. But notice the numbers on this graph. These are the tens to hundreds of cases in northern Italy, but that eventually also blew up. So I'm sitting around, I'm teaching in Switzerland for the last week of February, the first week of March. I ended up flying out about March 7th or March 8th. And it was really amazing to watch as we're sitting there, teaching and the students are taking classes. This outbreak is exploding across Europe. And in fact, I flew out on, I think it was the 8th to come back. I didn't fly back through Milan. By that time, Milan was closed down. The city was locked down. I had to fly through Zurich, and the students made it for about another week in that program before, if you remember, the CDC then raised the a threat level. I don't know what you call it, but the level in Europe to a point where the university had to close down all the programs, and the students all had to come back. But again, notice the graph, right? And think back to Wuhan. I remember back in January and February, we were thinking that's a huge outbreak going on in Wuhan. And then when we got to Europe, this was a huge outbreak. Everyone was highly concerned about it. But fast forward now. Here is a plot. And this is a plot of cases throughout the world, starting from January 2020, running through January 10th of 2021. So I just made this plot just recently. These are smooth lines of case counts again. Notice the y-axis. It goes from 0 to 300,000. And if you can see it at all, this little set of bars down here, that's the Wuhan outbreak. And that's what it looks like in comparison today to the black line right here is North America. The brown line right here is Western Europe. The blue line here is South America. This is sort of essentially by regions of the world in terms of total cases. And the Wuhan outbreak down here looks nearly inconsequential compared to what's happened since then. If you want to read more about this, by the way, this is all World Health Organization data that I downloaded. And in fact, I think this was in November, this got published in a statistical magazine called Significance. I had actually published this plot, but the plot was through November 1st. And if there's one constant theme throughout this talk, it's how fast things change. So I made this plot back in November. At that point, Western Europe was actually running higher numbers of cases than the United States, although we were on this upward climb. And they had just about turned this corner. And of course, now we can see they've come down, but who knows what the plot looks like out here now with the new coronavirus variant, for example. But again, to me, a year later, the magnitude of this side of the graph compared to the magnitude to this side of the graph is just absolutely striking. But we can drill down in here a little bit. So let's drill down into North America and see what the United States looks like compared to our sister countries here. So the red line is Canada, the black line is Mexico, and the blue line is the United States. So if you ask what is contributing, let me back up now, to the North America curve up here, guess what? It's us. The United States, in comparison to our two neighbor countries, is just massively different in terms of, again, this is number of cases. Now we could quibble over, this is again World Health Organization data, we could quibble over testing and whether Mexico is catching all their cases or not. But notice the dramatic difference. And even if we doubled or tripled, if we said Mexico's only counting a third of their cases, there's still really no comparison between these lines. It's really, really incredible to see the difference. And really, again, if we go back here, this is almost entirely the United States, what an outlier we are compared to the rest of the world in terms of numbers of cases, even adjusted often for population size. Okay, so from there, I wanted to sort of change gears a little bit and just talk about the question of how do you measure a pandemic's impact? So we could talk about cases, and that's kind of wrapped up in often a controversy about the question of, are you doing enough testing? How are you testing? Are you counting all the cases? Or are you not counting all the cases? And I was writing about this, and that would frequently be a question or a criticism of the question of measuring an impact of a pandemic by the number of cases. So I changed that a little bit and looked at the question of, what if we look at mortality? So what does mortality look like? In this case, it's the United States. And how has that changed since the pandemic has come into place? So what you're looking at in this graph here, again, it's time on the x-axis, and this is in weeks. So each one of these bars is actually a week. And on the y-axis now, it's not cases, but this is mortality. This is the number of people who have died in the United States, the height of the bar, in a given week. And what you'll see here is that varies pretty smoothly, sinusoidally, from a high in the winter time of around 60,000 people in the United States die per week to a low in the summer that's around 50,000 people. And of course, it bounces up and down. The black line is a model that attempts to model what that would be. And this is actually CDC data. Now, if you actually Google excess deaths CDC, it'll take you right to the page where I've gotten this data. This is data that is reported from the death certificates of people to their local health departments or the state health departments, then to the CDC, and the CDC compiles all those things and puts them together. But this is what's called all-cause mortality. So this is not COVID related. It's not any particular cause. It's everyone who has died. And so what they do is they in terms of trying to do surveillance in the United States, they model that. That's this black curve that's called the expected count. And then they look for deviation from that expected count. The expected count is what they think would happen if sort of history continued on. And then are we deviating from that in some way? And what you'll see, for example, this is in the late 2017, early 2018. We actually had a really bad flu outbreak in the United States. And in fact, so flu in the US on average kills about 30,000 people a year, plus or minus. A really good flu year, meaning it doesn't kill as many people, it might be in the teens, the number of people that die from the flu. In a really bad year like this year, it was around 61,000 people died from the flu in that year. So what you'll see is, in fact, that was a real anomaly. The blue code, or sorry, the orange code here and then the red code above shows the number that were above that threshold that we would have expected to see. But continue on over here, here's 2020. This is what we have seen in terms of death rates in the United States during this particular pandemic. There's a little bit of an anomaly here. So notice here we have a little drop off. Typically the last few weeks are sort of undercounted, meaning these are reports, again, that come from local health departments, to state health departments, to CDC. And there's a bit of a lag in that. It can be a few weeks lag, and it actually takes about a year to come up with the final numbers. So all of these numbers here are in the preliminary range. But nonetheless, it's really kind of striking what's going on, where we've gone through these three big waves. This is really sort of New York right in here, and what happened in New York. This is the outbreak we had over the summer. That was kind of in the Midwest, Southwest area. And of course, whoops, and this is what's going on right now where you've just got sort of things going on all over the country. If you add all these up, we're in the mid to upper 300,000 excess death range. which if you follow the news is relatively close to the number of deaths attributable to COVID, but really quite striking. And as I've written here, there's this really fancy Poisson generalized linear model that makes that little black line. You kind of don't need that line to see that the 2020 is a really incredible anomaly compared to past history. We can dig down into that. So drilling down, you could say, well, how's this break down by age? And so that's the same data going back to 2015 in this case. And each one of these bars is for a given age range, the number of people who died from 2015 up to 2020. And what you can see here is that for all age ranges, that black bar, the 2020 bar, is typically higher than all the others. The only place where it's kind of not is the younger ages. We were actually on a little bit of a downward trend here, and then we blipped up in terms of 2020. It's really quite a bit bigger in the older ages. So notice these are 45 to 64, 65 to 74, up to 85 and older, quite a bit higher. And of course, this has been in the news a lot because this is really where the counts, the number of people who are dying is much higher, much dramatically increased. Interestingly enough, though, if you look at the 25 to 44 year age group where mortality overall is down, right? That's, people don't die very frequently there. But if you look at the blip here for 2020 in that age group, that's actually the highest percent increase in mortality across all age groups. That increase is about 23.5% increase in mortality for those 25 to 44, whereas for the other age groups, it's in kind of the middle teens. So when you ask, where's the impact? Yes, many more older people are dying from COVID, but as a fraction of the population that dies, it's much higher actually for younger age groups, which actually surprised me when I ran these numbers. If you look at by race ethnicity, same data. This is just now for the percent change for 2020 versus 2019 mortality. And we look at Hispanic populations or the non-Hispanic Black, White, Asian, or American Indian, Alaskan Native populations. The striking thing here is that the non-Hispanic white population, the death rate is dramatically lower than all other non-white populations. So ignoring others, which kind of is a strange mix of white, multiracial, all kinds of things, if you compare to the other ethnicities, in fact, if you're African American, you're Asian, you're American Indian, Alaskan Native, the death rate, the change in death rate, the percent change is about 3 times higher than it is for the white population. And if you're Hispanic, it's nearly 5 times higher. So really a dramatic disproportionate impact on the minority population, the non-white populations in the United States. So how am I doing on time, Doug? Another 5 to 10 minutes, you think?
Oh, sure.
Okay, all right. So I wanted to switch gears again a little bit and just talk, now we'll get a little more into statistics rather than just the data, is to talk about some of my experiences here at Virginia Tech and a little bit of modeling, just a touch of modeling. And like ASU, like every university around the country, last summer, we had, I don't know about ASU, but at Virginia Tech, we actually closed down after spring break and put everything online as everyone was really worried about the pandemic's hit. Come summer, we were then trying to plan for what do we do in the fall. And I was part of a team of faculty and administrators looking at that. And in fact, we were tasked to sort of try to model this out, try to figure out what might fall look like so that the administration can figure out how are we going to handle that? What do we need for resources? What do we need to change in procedures in the university to be able to operate? And what does that mean? So we spent the summer making lots of models and making recommendations to our administration about how we ought to think about operating. And what this slide shows you is 2 things. And let me talk through it a little bit and then explain why I've got it up here. The bars here are in fact the actual number of cases that occurred in the New River Valley. So the New River Valley is 4 counties in a city. I guess I don't know how you count Radford, Doug, but it's
a city.
Yeah, so it's 1 city and 4 counties is our sort of our public health area. That's called the New River Valley. And so these are the cases in the New River Valley over time. So starting this is March 22nd, and this is all the way out to early November. So you can see how the cases progressed in our little local area here over time. And of course, we were down here in May and June and July trying to plan for what was going to happen out here. And by the way, notice in our case, we're a very rural area, and we were really lucky early on in the pandemic. So, this is sort of when the big outbreak was occurring in New York City, right? And we were well insulated, it being way down here in Southwest Virginia in the Appalachian area. It hit Northern Virginia pretty hard somewhere in the, late spring, early summer. There was a big outbreak in Northern Virginia, but it didn't really make it down here to us. So we were actually well insulated for a while in our sort of little rural area. So, but still, we're thinking eventually this is going to reach us. So we built some models. Let me say, first of all, I guess what happened, and then I'll talk about the model. So what you'll see here is, somewhere here it was late August and then early September is when classes started. Students were moving in late August, and I don't remember what the first day of classes was, but it was either late August or very beginning of September. And what you can see, in fact, is the case numbers begin to climb. And in our little area here, the total population in Montgomery County, which is where the university is located, I think is about 100,000 people. And, the undergraduate population in Virginia Tech is 30,000. So the undergraduates are a really large fraction of our population. And of course, everyone was very worried about what was going to happen when they came back. Well, when they came back, in fact, no surprise, we started to see case counts rise. It was more people in the area at the very least, never mind the fact that we had them in dorms. And of course, in these kinds of conjugate settings, it's easy for the disease to spread, or easier. So we started to see case counts climb. And in fact, I remember this week, September 6th, very well, because our model showed that either we were going to be successful and with a lot of effort control it, or maybe we were just going to lose control and it was, we were going to have to shut down and put everything online. And September 6th was when we had started up the epidemic curve, and you can see it climbing. And we were thinking, what does this week look like? Is it going to be up here, or are we going to turn flatten the curve, as we were saying back then? And we were doing a lot of things as a university to try to flatten the curve. The students were working hard at it. And you may remember back in this early time right here, when the university was opening, people weren't sure about what was going to happen, right? They were very worried about what was going to happen. And in fact, I think there was sort of a fatalistic sense in many places that, look, there's no way we're going to control this. So let's go, particularly for some students, let's go back, we'll party for 2 weeks, they're going to shut us down, but we're going to enjoy ourselves, and then we're going to be gone. And there was a bit of that effect going on in here too. But in fact, we were successful. So you can see that the curve actually did flatten over right here. And in fact, we turned it down, and we successfully went through the whole semester. Again, most classes were online, but students were in residence in the area. But notice the difference between those bars and this black line, which is a projection from back in September 20th. That's what, in fact, a model was projecting would happen. In fact, that's what a lot of our models, this wasn't our model, but a lot of our models looked a lot like this as well. And one of the reasons I show it is just, you have to think about what you're assuming in a model. And I was working very closely with a public health person who said, and we had very different viewpoints. It was really a wonderful collaboration, because I think of a model and I think about predictions and I think what went wrong. She said, I'm looking at this model and I'm asking, what public health interventions can I put in place to not have that happen, right? How can I change the future so I don't see that curve? And in fact, she was exactly right about that. But I mentioned this on here because on our Department of Public Health, Virginia Department of Public Health website, they were showing this curve, and they were not showing the actual data on that particular page. And somewhere about, what is that, September 20th, I guess, people were looking at this curve and going, oh my God, like we are exploding in this area. We've got all these cases going on, not realizing this was a model projection that was wrong. That in fact, we had, if we hadn't done anything, sure, we would have been here, but we were actually here. And so there were actually a whole bunch of public relations news articles that kind of went out to people and said, whoa, stop worrying about this. That was a projection that is incorrect. We've been very successful at turning the curve, and here's what it really, really looks like down in here. So that was really quite interesting, and I think really good news for people. This model, by the way, gets fit every week out here. So every week we observe some more data and they fit the model. And so this was now a month later. This is what the model looked like. Here's the actual data again. Here's the model itself. And I put up George Box's quote. Doug, I imagine you've used this in class.
Oh, yes.
Famous, maybe the most famous quote in statistics, right? All models are wrong, but some are useful. In fact, if I back up, this model was really quite useful because we were talking about this at the highest levels of administration of here's what happens if we don't do stuff. So let's do stuff, right? So we knew we wanted to make the model wrong. And in fact, it turned out like this. Now, interestingly enough, in this particular case, this model was wrong too, because it was fitting sort of pretty well what we did. This is all retrospective, but it projected we're going to keep going down. Well, in fact, that didn't happen either. In fact, we flattened out and stayed at a fairly constant rate for the rest of the semester of around here. So we got the rate down, but we couldn't get it all the way down. And then just the next slide, this is what the data looks like. I guess it was as of this weekend, I pulled this data. So this is right off the Virginia Department of Health's website. The left side are case counts, again, in the New River Valley. This is daily case count though, so it's kind of noisy. But if you just follow the yellow line, you can see here was when we opened up last fall, and it came down, but it didn't stay down. In fact, you'll notice it's really creeping up, and it's been creeping up even since the semester ended. We've gotten more and more community spread going on outside of the student population. In fact, the students weren't even here at this point in the curve. So we're really in an interesting place right now. The model, here's the model result. And here's, again, by the way, left side, that's daily counts, right side in the model, it's weekly counts. So the scales on the y-axis are different, but the patterns are about the same. Here is school starting up in the fall. It continues to creep on up. Notice here's about where we are right now. Interestingly enough, I would say, again, this model is wrong. That is, this linear, where's my pointer? This linear trend right here is community spread. That's probably going to keep going. And this week we are opening up again. So the big question is, do we get a bump like this again? That is, do we see this again in the spring, or does it just kind of keep going up with community spread? This part right here, I would say, is almost surely wrong in this model. It's being overly optimistic at this point about how we're going to bring this curve down. So a really interesting set of things there. Last slide. And that's just, I wanted to just sort of say to everybody in the class, you're learning about statistics and the scientific method and a lot about experimentation, and that's wonderful. What I'd like to propose to you is to take those ideas, not just the mathematics, not just doing a t-test or doing an ANOVA, but take those ideas into both your professional and personal life. They're really important. And it's this idea of statistical thinking about things and thinking about evidence and empirical evidence that you want to take into account. And what I want to mention there is the fact that, again, if going back to my experience as we went through last semester here at Virginia Tech, there were a lot of people who had very hard and fast ideas about what was going to happen. Either we're going to shut down in a week, and some people were like, lots of people are going to die. It was really sort of doomsday scenarios. Other people, there's nothing to worry about. Why should I wear a mask? Nothing going on. I think one of our successes for us in making it through this was being very mindful of what does the evidence show. And both of those two extremes were not correct, right? It was something in the middle where day by day we looked at how many cases do we have? Where do we think it's spreading? What do we have to do to fix that? And that's really about being very scientific in your mindset and being very careful about thinking, what's the evidence? Not what do I want the evidence to be, but what actually is going on? And then what in this case, what could I do about it? So I put that forward as something I think that's good for you in your personal life as well as your professional life. And I think, Doug, I'll stop there.
Ron, thank you very much. I really appreciate your presentation. And a kind of a follow-on to the point on your last slide. I can remember reading years ago something that was written by H.G. Wells. And of course, we know H.G. Wells was a famous writer of what we would think of as science fiction. Probably the War of the Worlds is probably his most famous piece. But he actually wrote in some article someplace, and I've lost track of exactly where, he wrote that the day would come, and this was early 1900. Okay, he wrote that the day would come where a knowledge of statistics would be as important to effective citizenship as the ability to read and write. And I think your last slide is nailing that very point in an extremely contemporary way. We're seeing that today.
I think that's
By
so
the way,
well said.
we have lots of questions. We have lots of questions, and your talk extremely timely, and some of them relate to the experimental design course, and some of them relate to other things. So let's if you'd like to stick around and help me roll through these questions, we will see what we can do.
I will do my best and follow your expertise.
Well, here is a really interesting question, and he's talking about the paired t-test. He says when we try to reduce the differences in specimens, which are called noise, by blocking them, and he's studying earthquakes in a lab, and he works with rocks, and in nature they are of course not the same; they're heterogeneous. And at each test, the samples will break, and then we have to test a new rock for the next experiment. And so the best we could hope would be to choose rock samples from almost the same block and hope they're similar. But when we go to study these small earthquakes in the lab, the small differences make changes in the results. Some parts of the specimen are weaker than others. And so these differences are not easy to avoid. And so are there other ways to block the noise coming from different specimens for each test batch? Well, obviously, if you can make the specimens large enough to do both tests on the same piece of material without breaking it, that would be ideal. But if you can't, another strategy is you might be able to measure some property of the sample, such as its strength, or size, or some measure of the specimen, and then treat that as a covariate, so that so you have a covariate that's varying along with the response, and that covariate is a property of the sample material. People do that in agricultural experiments a lot. If you're feeding cattle, let's say, different feeds, and you're trying to measure the weight gain, then the covariate would be the initial weight of the animal. And so my guess is maybe something like that would be useful. I don't know, just a thought. Do you have anything that you could add to that, Ron? Anything? Does anything come to your mind?
Maybe just to illustrate the problem more than it is. I think your answer is right on target. But in fact, that's going to become a little misnomer there, meaning this happens a lot when you're doing destructive testing. Basically, right. You test it and you break it, and then you can't test it again. I've had experience with that. We did that in military bulletproof vest testing, and it was the same problem. You have a plate, you test it by firing a projectile at it, and once you tested it once, you can't then test it again because you've basically destroyed the plate. So yeah, I think, and in the worst case, if you don't have a covariate, then you're just kind of doing a 2-sample t-test, and you have to live with that noise and trying to get a big enough sample to overcome it.
In fact, that's the only recourse, is to take a large enough sample to try to overwhelm some of the noise. Yeah. And now here's a question that I know nothing about. Okay. How does biomimicry, help with regards to ocean engineering?
Wow.
I don't know so much about biomimicry. I know a little bit about oceans, probably not nearly as much as you do, but I don't really have a good idea here. Does anything come to your mind, Rob?
Not really, not specifically either, but I think maybe the idea of the question is, and I think it's a good strategy. You're designing things, you're engineering things. Often Mother Nature has already figured out some good solution in the biosphere, whether it's in the ocean or elsewhere.
Right.
And copying that in some way or trying to mimic that in some way can be a good engineering strategy. But short of any other details, I can't say more than that, I don't think.
Yeah, this is a question that if our participant would provide more detail, more information, then maybe there's something that we might be able to do in terms of some guidance. And so again, great question, but probably not enough detail. Okay, so another question. A great explanation of Taguchi's crossed array design. in the lectures. And so far as I've understood, one of the drawbacks is the very large amount of experiments. My colleague, though, has mentioned Taguchi's name in regard to some small designs, like 15 samples for 7 to 9 factors. But unfortunately, she can't remember the reference. Are you aware of any small designs developed by Taguchi? Well, this is discussed in the textbook, and he did promote the use of small designs like 9-run designs, 12-run designs, 16-run designs, and many of them are standard fractional factorial designs. Many of them are standard fractional factorial designs, but where he sometimes ran into trouble with these designs was putting lots of factors in the designs so that the fraction was like resolution 3. And so the amount of information that you got, the main effects were all confounded with interactions. And so it made the interpretation of the designs difficult. And the other place that I think he got into trouble was the use of signal to noise ratios. And there's a big discussion of that in my textbook. And in fact, if you really want to get a lot of additional insight on some of this, there is a panel discussion that appeared in Technometrics back in the 90s that was edited by Vijay Nair. And the reference for that panel discussion, I don't have it right in front of me, but it is in the textbook. And that's a very good source for finding more information about this. There's also a very good article that Stu Hunter wrote in Quality Engineering called Let's All Beware the Latin Square. And it also talks about the Taguchi's small designs. And that reference is also in my textbook. So yeah, there's lots of stuff out there that you can get to. And if you can't find that in the textbook, let me know and I'll point you in the right direction. Okay, you mentioned that the recent edition of your design analysis experiments book has a lot of electronic format with additional media materials. I'd like to have 1 or 2 paperback books on design. Well, there is a paperback version of my textbook. Wiley will provide a paper version of the book that is essentially a full copy of everything that's in the ebook. So you can get that directly from Wiley. There are also a couple of other paper books that I highly recommend. One of them is the Minitab supplement that goes with my book. This is a very good book that takes you through a nice expository discussion of design, and it shows you with a lot of detail how to actually use Minitab to solve a lot of the problems that are in the book. And there's also a jump version of that same book, and you can find those typically by going to either the Minitab website or the Jump website. And I highly recommend those. Those are very well done by people that really know what they're doing, and they give you a good intro to how to actually use the software to do this, which gets you very operational. Okay, another question: is it allowable to use the examples from your course in my own lectures and presentations with proper reference? Sure, I have no problem with that, not at all. That'd be great. Okay. Oh, here's a response surface question. I am designing experiments for an RO membrane rejuvenation project. I skipped screening and got the required information from the literature. Narrowed down the factors that are influencing the response to 2 and chose RSM. Due to operational limitations, I thought it would be appropriate to use the inscribed method with 5 center points and 3 replicates. The tabulated experimental runs, I have to conduct 20 runs for 1 center point out of 32 runs. When I compare it with 2 different software, Jump, Design Expert 12, I realize it's possible to decrease the center point for axial runs. I'd like to know the following. Number 1, is it suitable to skip screening experiments when we have the experimental conditions in the literature. Risky. I can't tell you the number of cases where I've seen people run experiments that things didn't come out quite the way they liked, but they didn't do any screening, and they only relied on the literature. They didn't take into account the specifics of the kind of situation that they were in. So yeah, you can maybe get away with this, but it's tricky. Is it possible to cut the center point experiments? I don't much like that. I like to make sure that the number of center points is large enough to give me a good prediction variance profile across the design space. One of the things you can do with JUMP is you can look at something called a fraction of design space plot, and you can get a pretty good idea of what happens when you add or remove center points. You want to have a prediction variance profile that's pretty flat across the design region. And if you cut back a lot on the number of center points, you get big prediction variance in the middle of the region. and you probably don't want that. That's probably where you want to make the most accurate predictions. With JUMP, blocking in, say, an inscribed CCD is not possible. What are the drawbacks of the DOE without blocking? Well, if you have nuisance variables, it can be devastating. I would, if you think you have nuisance variables, different materials, different time periods, different operators, different pieces of equipment, always try to use a design where you can do blocking. Always try to use a design where you can do blocking. It looks to me like the situation that you're in might be one where an optimal design would be a good alternative to some variant of a CCD. So think about an optimal design, because you may, with only two factors, 52 runs seems like a lot. Okay, 52 runs seems like a lot. I would be looking at more likely a design that has somewhere between 18 and 20 runs as a starting point. So think about a custom design. Think about say an optimal design. I think I would be sort of focusing in that direction. Ron, do you have any thoughts on that?
I do not. I defer to your expertise entirely.
Well, I just wondered, because when I see people starting to ask questions like this, I always start thinking optimal designs. Okay, I have a question regarding using cross-sectional methods, such as binary logistic regression, on time series data. Is it legitimate to average time series data points and then apply binary logistic regression versus some sort of interrupted time series design? Well, you can do that. I guess when you average them, what you're getting is a proportion, or something that's a 0-1 indicator variable, or some kind of place where this is one where I'd probably have to look at the specific application to get a really good feel about the answer. I've always been a little bit nervous about summarizing data like this and not working with the individual observations. Sometimes I feel like I lose information. Does that make sense, Ron?
It absolutely does. Yeah. I mean, and you're not accounting for that lost information, right? By averaging it, so yes, I agree.
Yeah. I think you run the risk of losing information. And that, but again, if you give me some more specifics, I might be able to help a little bit with that. And then, is there a way to simplify a strip plot? Okay, a strip plot, because I'm trying to pronounce this here. Design to get a more robust estimate of each of the model terms. Well, you can. About the only thing you can do and I'm going to say to try to get a more precise estimate of each of the model terms. would be to increase the number of either whole plots. I mean, that gives you a better estimate of the whole plot effects. But I'm guessing that that's probably what you would have to do. Multiple non-normal distributions. And using the Kruskal-Wallis test, can you use the H statistics from the KW test to rank the various non-normal distributions? That's not a, I don't know, that's not a bad idea. You're trying to sort of compare these distributions to the normal. So that maybe is a way to do that. Does that sort of make sense to you, Ron? It doesn't look like a bad idea to me.
Yeah, I don't know what what do I want to say? I don't know what the downsides are. Meaning, I'm not quite sure how that comparison works. I want to think about that and maybe look into that more carefully.
Yeah. I'm not sure how. I mean, how you could always look at other measures like moments. And say, well, okay, how, particularly let's look at the first 4 moments of the distribution, and how do they compare to the normal? And maybe there's some distance metric that you can think of relative to that, which would be appropriate. Good question.
Yeah, I noticed he put the word rank in quotes, and that's kind of what I'm really thinking about. Is what does that mean? What does that rank? So.
Yeah. Is there any way to make hypothesis tests in time series? Looking for an alternative to causal impact analysis. Yeah, there are lots of statistical tests that you can do with time series data. A lot of these tests come in the general category of what in time series analysis we call intervention analysis. You've got a time series, and at some point there seems to be a change in the evolution of the time series. Well, there's a technique called intervention analysis, which you can use to see whether the statistical properties of the time series before and after this point are the same. And that's one way to do it. Ron, I think of a lot of statistical process control tools as being ways to answer this kind of question.
I was kind of thinking of the same thing.
So
you may have to do some transformations or something. It depends on the time series, I suppose, but that's
part
of what those methods are all about.
But looking for change points, looking for shifts in level or shifts in variability. SPC methods are another whole class of techniques that you can use to investigate that kind of situation. And then there is this tool in time series analysis called intervention analysis that is extremely useful in a lot of situations. Okay, out of time. We got to shut down, but please, if there's questions that we didn't get to, we'll take a look at these and we'll get some answers put up in Coursera for you. I hope you've enjoyed today's talk. I want to thank my guest, Ron Fricker, so much for taking time out of his busy schedule to visit with us. And we will be back again for another Fireside Chat next month.